All right. Well, if you're joining us on Zoom, welcome here to Thursday's class. It's 12:30, so I'm going to go ahead and get started. We've been working out of chapter 11. We're going to continue to do that today. And I think get through most of chapter 11, if not all of it, okay? Because we just have to consider something called molecular orbital theory at this point, which is the second half of chapter 11. So that'll make a nice break point as we look towards next week, okay? Now, a few things here, announcements, I guess you can say, getting close to the end of this semester. I can't remember if I mentioned this to you all last time or not, but the other day I got an email in my email box complaining about my usage of Zoom cloud memory space, okay? Because I had a lot of videos up there. So anyway, the limit that they set for the account is very, very low. Basically, like I could record one day's lecture for all my classes and that's about it, maybe. So what I'm going to have to do is go and delete a lot of the pre-recorded lectures. So if you have been wanting to look at a particular day's lecture content again, to take better notes, or you just missed one, I'm going to encourage everybody to go back and do that more or less right away, because these videos that are posted up there in length of the previous recordings are probably not going to be there much longer. Okay, so that's the first thing. Now, the second thing is, the end of the semester is really sneaking up on us here, and I'm trying to emphasize that to everyone. Think about your assignments that are due here at the end of the semester. Now, for y'all, you just have this final exam, so I'm sure everybody's aware of that. It will be comprehensive over the entire semester. But in addition to that, you've got these online homeworks on Connect, okay? So if you have not been completing those, if you've fallen behind a little bit, I'm going to encourage you to really spend some time here this weekend and next week. Try to complete all those Connect homeworks. You don't really want to leave that hanging long past Thanksgiving. The reason being, I think all those are due December 2nd, 11:59 p.m. And that's kind of a quiet, uneventful date. It is the last day of classes, okay, at midnight. But it's really easy to forget about those Connect homework assignments. And I'll tell you, we can't really do any extensions or makeups after that day. Because we will rapidly move into the grading period, and we have a short amount of time to put everybody's letter grades together and enter them in. So that'll be a busy time. So we can't really do makeups or extensions, okay? So the point is that you don't want to get accidentally caught, completing, only 40, 50% of the Connect homework. That'll really, really hurt your grade. So please, maybe put a reminder in your phone. You can ask Siri or whoever your phone's personal assistant is to remind you, maybe like Saturday after Thanksgiving or something like that, to do your Connect homeworks. I don't want to see that happen to anybody. And it seems like every semester, there's a certain fraction of students that this kind of happens to, and it ends up hurting their grade, and nobody wants that, right? So make sure you schedule some time for that. And other than that, I don't think there's much else. I think we got things pretty much under control, other than we got to take this final exam and answer some more questions correctly, right? So towards that goal, we should consider chapter 11 or continue on in chapter 11. Now, at the tail end of class Tuesday, we talked about two different types of covalent bonds, and we kind of learned some new terminology: sigma bonds and pi bonds, okay? Sigma bonds are formed from the so-called end-on-end overlap of orbitals, okay? Any single bond are sigma bonds, okay? They always form from this end-on-end overlaps of orbitals, whether they're atomic orbitals or those hybrids that we talked about in the valence bond theory. But a pi bond is different, because a pi bond is formed from sideways overlap of orbitals. Like if you have, two p orbitals, these are the ones that are dumbbell shaped, and they overlap side on side. That's an example of a pi bond. That's an example of a pi bond, okay? So these are our two types of bonds. Now, if you've got a double bond, that consists of one of each. One sigma, one pi. The first bond's sigma, the second bond's pi. And if you've got a triple bond, That's 1 sigma and 2 pi bonds. Okay. Now, whenever you have a pi bond in a molecule, rotation is no longer allowed with respect to the atoms. Okay. And that's important to understand. And again, once you get on to like organic chemistry, that'll be like super important to understand. Okay. Because different chemicals, remember, we talked about isomerism last time, or cis-trans chemicals here. Where was that? There, these two. Or these two chemicals are different. And the reason why is because there's a double bond in the middle between the carbon atoms, and that locks the configuration in place. And that's kind of a big deal in organic chemistry, all right? So we talked about that last time, and we said that sigma bonds, those are our single bonds, overlap of our sp3 orbitals here. In ethylene with the double bond, we've got 1 bond forming from the overlap of the sp2 hybrids. And then the second bond forms when our unhybridized p orbitals on the central carbons overlap, okay? And that's our pi bond. And then the triple bond in acetylene, this is a very common fuel, sometimes used like for welding and torches and things like that. Okay, acetylene C2H2 has this structure right here. That's got a triple bond. So it's got 1 sigma and quantity 2 of these pi's. So the sigma is formed by end-on-end overlap of an sp hybrid on each central carbon. And then our unhybridized p's form a bond, a pi bond, there and there. There's the red and the black here, and that's because there's 2 sets of unhybridized p orbitals. So they both can overlap and form 2 pi bonds, each one, the red and the black, being 1 individual pi bond, okay? So that's kind of where we left off last class. We actually made quite a bit of progress last class. And then today, what I'd like to do is to move on and talk a little bit more about the second half of chapter 11, which is going to be based in something called molecular orbital theory. And we're going to kind of give an overview or an introduction to this. This is another major theory of covalent bonding in chemistry. And this one, it's sort of its highlight or a reason why it's good or why someone would be interested in this is it really allows us to understand energetic properties of molecules, specifically light absorption. We can talk about these molecular orbitals, and we can send an electron from one molecular orbital to the other, just like we can in atoms. And that explains light absorption and light emission. That's very useful. So this one kind of shines in the energetics of molecules, okay? And it's also a really good model to understand bonding in molecules and whether or not, so we're going to use this in a little bit to predict whether or not certain molecules are viable, so whether they could exist or never would exist, okay? And we can actually predict that once we get good at this molecular orbital theory. So it's good at predicting bond orders and whether molecules would be held together at all. And it's also really good at predicting magnetic properties of molecules, not just atoms, but molecules, okay? Collections of atoms. We can predict whether molecules are diamagnetic or paramagnetic. And those are words that we saw earlier this semester having to do with the magnetic properties of atoms. And it has to do with whether they have unpaired electrons or not. Well, we're going to be able to do that for molecules here in a little bit, with this invoking this MO theory. So that's kind of where we're going and what the major advantages is. Okay, so now we know a little bit about where we're headed. Let's talk about what MO theory is really all about. Okay, so in MO theory, basically what we're going to do is we are going to combine what are called the wave functions of individual atoms that make up the bond. Okay, and we're going to do that through an approach that's called LCAO. We're not going to do that, but it's typically done. And this stands for the linear combination of atomic orbitals, okay? Now these wave functions are complex mathematical functions that serve to describe our positioning of electrons in our atoms, okay? So what this LCAO approach, linear combination of atomic orbitals, is basically going to do for us is we're going to take two atoms, bring them close, and make a bond. And when we do, we're basically mathematically going to combine or sum or add these wave functions for the individual atoms. That's more or less what this boils down to. We combine the atomic wave functions. And when we do, we combine them together, we're going to form a molecular wave function or molecular orbital. Okay, so we're kind of taking this idea of atomic orbitals, like the S and the P and the D type orbitals. We're saying that we're going to combine mathematically those orbitals to make molecular orbitals now. That's more or less what this whole process involves, okay? But the thing is that we know that our electrons, say for instance, have wave-like behavior, okay? And waves, kind of think about an oscillation, right? They always exhibit, we'll say, a phase, okay? And maybe we abbreviate that phase or describe that phase as a positive or negative, okay? Let's think about that in your head, like positive going wave or a negative going wave, okay? So it just so happens that when we combine our wave functions mathematically, or when we add them, two things can happen. One, we can add our atomic orbitals together, we'll also call in phase, and that leads to what we're going to refer to as a bonding molecular orbital. So if the atomic orbitals combine in phase with one another, what that does is it increases the electron density between the nuclei of the atoms in question. So atom A on the left, atom B on the right. If we add together our atomic orbitals and the orbitals are in phase, between the two nuclei, the probability of finding an electron goes up, okay? And that actually leads to a chemical bond, a covalent bond. So addition in phase leads to what we're going to call a bonding molecular orbital. And as the name suggests, that's good for holding the atoms together because we have a higher electron density between the nuclei, and that's what's required to make a covalent bond. But the second thing that can happen is if our atomic orbitals combine out of phase, we subtract the two, which leads to one of these nodes between the atoms. So the one atomic orbital will essentially kind of like cancel out the other one. It leads to a node. Now, what is a node again? Well, it's a region of very low probability, essentially zero electron density between the nuclei. And if that's the case, we do not have a, well, that's not good for covalent bond, we'll say, okay? Now, because that's the case, because this node would exist between the nuclei, and that would be bad for covalent bonding, we're going to give this orbital, the one that results from subtraction or out of phase combination, we're going to call this the anti-bonding molecular orbital. So we're going to have two different types of molecular orbitals or classes. Bonding, the bonding molecular orbitals, where again the wave functions, the atomic wave functions combined in phase. That's good for covalent bond formation. And the other one is bad for covalent bond formation. It's called anti-bonding, okay? So maybe you kind of see what we're doing here already. I mean, we're going to take two atomic orbitals on adjacent atoms, one from atom A and one from B, combine them together, and ultimately it turns out we're going to make two molecular orbitals. One's going to be in phase, the other is going to be out of phase. We're going to make a bonding and an antibonding. So if you combine two atomic orbitals, you got to get two molecular orbitals. The number of orbitals, again, are still conserved, just like we saw last class with the valence bond theory, where we had to make the same number of hybrids as atomic orbitals we used. Okay, so that rule is not really going away. All right, so we're going to create bonding molecular orbitals. Anytime you see this MO, it stands for molecular orbital, okay? And anti-bonding molecular orbitals. Bonding is good, anti-bonding is bad. Now, this is kind of what I was telling you about a second ago, where you could think about waves, right? Combining in phase or out of phase. So if they combine in phase, that's our bonding molecular orbital. If they combine out of phase, it's an anti-bonding. That'd be like if waves cancel, like destructive interference in physics, you call that, right? Okay, so this is just a slide that, again, kind of reiterates that. All right, so now what I'd like to do is spend a few minutes talking about specific substances. And we're going to start talking about bonding in H2, hydrogen gas, H2, right? Seems like a good place to start. Seems like a simple enough molecule. So to begin this discussion, we're going to consider two isolated hydrogen atoms. Now, these are not bonded together quite yet. It's just a hydrogen atom, so it's got one proton and one electron in each atom. And now what we're going to do is we're going to start to allow these atoms to approach one another. Eventually, covalent bond's going to form, okay? So from this molecular orbital theory perspective, what could possibly happen for spatially, all right? Well, if these atoms approach one another, we could see the wave functions for the individual atoms to combine constructively or in phase. And if they do, we follow this bottom path to make a bonding molecular orbital. Okay, so we're going to add, this leads to constructive interference, this region right here and through here really, between the nuclei. Will the density of electrons there will increase from the separated case? That leads to covalent bond formation or supports covalent bond formation. Now, because the electron density increased between the nuclei, it turns out that's energetically favorable. So if we look at a plot of potential energy, the isolated atoms would be like here, sort of in the middle in the scale. Now, this is a non-quantitative scale, but it's meant to be like pseudo-quantitative, right? Maybe that's like a zero energy. But as these atoms approach, if they combine in phase, the energy of that bonding molecular orbital is reduced. And now it's down here somewhere. That's our energy of our bonding molecular orbital. Notice it's lower, a lower energy state. And that's ultimately why, if you put electrons into that bonding orbital, you can hold this atom together, or hold the molecule together, okay? So that's kind of where we're going with this. Now, the opposite thing can happen. What if the isolated atoms come together and their molecular orbitals, will say, combine out of phase, destructive interference? That leads to one of these nodes between the nuclei, a very low probability of finding an electron there, essentially zero. And that's really bad for bonding. And indeed, the potential energy of that state would be way up here. That's our anti-bonding molecular orbital, okay? So we have a bonding and an anti-bonding, in phase and out of phase. Now, there's some like designating terms or abbreviations for these orbitals that I guess we should get into talking about at this point, okay? Now, just like before we had sigma and pi bonds, that's kind of actually not going to go away here. We're still going to use that concept in molecular orbital theory as well. And notice that down here, you've got a sigma 1s, and here sigma asterisk 1s. It turns out those are the abbreviations for the bonding and the anti-bonding molecular orbital. Whenever you have that asterisk, that tells you it's an antibonding orbital. Without the asterisk, it's a bonding, just by as a general rule, okay? So that's basically what these abbreviations tell us. Now, beyond just telling us whether it's bonding or antibonding, it does a few other things for us as well. One is it tells us that here we are dealing with a sigma type bond, aren't we? And indeed we are. Because we have our hydrogen atoms, they would be 1s1, 1s1 in the atomic sense. We overlap the 1s orbital. This is end-on-end overlap. This is a sigma type overlap. Okay, so it's a sigma type molecular orbital, sigma type overlap. And it's formed from the 1s atomic orbitals. So all that information is provided in the label for the molecular orbital. Okay, the lower energy is the bonding, the higher energy is anti-bonding. The bonding molecular orbital usually contributes, putting electrons into the bonding molecular orbital contributes to holding the molecule together. Putting electrons into the anti-bonding orbital does not contribute to holding the atoms together. And ultimately, that's going to help how we're going to be able to predict whether or not certain substances stay together and bond or not. You'll see that here in a few minutes, okay? Now, based on this theory that we've been talking about, what we're going to be able to do is write molecular orbital diagrams. Now, this is for the molecule as a whole, but what it's going to work out to do for us is something a lot like we did with atoms. Remember when we wrote those box diagrams for atoms like 1s2, 2s2, 2p6, and we started to fill electrons with the arrows into the boxes? It turns out we're going to do something really, really similar here. But instead of using atomic orbitals, like the s and the p and the d, now we're going to use molecular orbitals, like the sigma 1s, the sigma 1s star. We could even make some out of p-type atomic orbitals. We'll get to that here in a little bit, okay? But we're going to build these molecular orbitals, which belong to the molecule as a whole. And we can fill electrons into them instead of putting our valence electrons into these atomic orbitals, okay? And that's what this is going to look like here in a few minutes. In addition to having molecular orbitals shown in our diagram, the diagrams that we're going to talk about, and this will become more apparent once we actually talk about it, show an example, okay? But they also show the atomic orbitals from which we generate our molecular orbitals. So we know where the molecular orbitals came from, and that's an important part of the diagram. We'll talk all about that as we go. And I keep alluding to this last point, okay? But this is one of the fun things, I guess, you can do with this molecular orbital diagrams. You can compute bond order from a completed molecular orbital diagram, energy level diagram, which we'll see here in a second. We can calculate it as taking 1/2 times the difference between the number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding. So it turns out that we're going to put electrons into these molecular orbitals in our diagram. And again, we'll show you how to do that in a second. And once you fill up your molecular orbital diagram correctly with electrons, you can actually calculate bond order through this equation. And what that does for you is it allows you to predict whether or not a certain molecule or ion would be stable or not stable. Okay, that makes sense? That's kind of like what this is going to do for us here. Now, I'll show you, let me clear this, and then we can show you kind of an example of that. Let me see where this slide starts from here. Okay, H2, that's what I was going to go to. Good. Okay, so we're going to return to H2 for a second. Okay, now we know hydrogen gas is a stable substance, right? H2 gas, it exists. Maybe it's flammable, but you can bond it together, right, and make H2. That's what we mean by exist, okay? If we draw its Lewis dot structure, it would have something like this. It's a duet, of course, because that's all hydrogen needs. Now, from a perspective of molecular orbital theory, we take our 2 atoms of hydrogen. And in diagrams that we're going to look at today, these are our molecular orbital energy level diagrams, is what I call them. There's different parts to this diagram. I guess it's important to start there, okay? So what I'm going to do is I'm going to kind of draw this dotted line here and then one over here first to explain the, 3 different regions of the curve. It depends how you want to look, or 3 different regions of the diagram. It just depends how you want to look at it, okay? But to the left of the first dotted line is kind of the space that we devote to atom number 1 involved in the bond. And then in the space to the right is atom number 2. Okay, so what I'm saying, we're starting with the simplest possible case here, like H2, right? Over here is one of the H atoms, and over here is the other H atom. Okay, that's kind of like its space or where we start. And when you're drawing these diagrams on your own, that's kind of what you would always start with, okay? your individual atoms, and then what you do is you write a box. And that box represents an atomic orbital, not a molecular, but an atomic orbital. Same thing over here. Atomic orbital in the valence shell for the atom that you're going to bond together. So here we're bonding H2, so there's H on both sides. And because it's H, we've only got the 1s level. That's all we got to use, right? So we got one box on each side. One box only. And that box is representative of the 1s atomic orbital. This is the second atom. Over here is atom number 1, or the first atom. Everybody see that? Now, usually, when you're drawing one of these diagrams, you put those boxes vertically kind of in the middle. Like up and down, you put those kind of in the middle. And the reason why is because these diagrams are always generally written such that this kind of like imaginary y-axis, up and down, is energy. Okay? So anything you draw really high on the diagram is at a high energy condition, and anything you draw really low on the diagram is meant to be a low energy, potential energy condition, okay? Now again, when things bond, they like to lower their energy, so we're trying to get the lowest possible energy, and we'll see that here in a second, okay? But when you're drawing in these boxes for the atomic orbitals, you tend to put them somewhere kind of in the middle, okay? Make sense so far? So left side, atom 1 in the bond, far right, atom 2. And I have one bond that we're considering here. Now, what about in the middle? There's all this other stuff in the middle. Well, we kind of talked a little bit already in class today what we might put in the middle. We're going to take these hydrogen atoms, the one on the left and the one on the right, we're going to bring them together. That means that their 1s atomic orbitals will begin to overlap. When that happens, they can combine, their wave functions can combine in phase or out of phase, additively or subtractively, okay? If they combine additively in phase, we create the bonding molecular orbital. It's a sigma type overlap, end on end. The bonding molecular orbital was made from 1s atomic orbitals, okay? So that's what we're going to call it, the sigma 1s bonding molecular orbital. Now this molecular orbital belongs to H2, the molecule as a whole. Because to generate it, we basically have to bring these atoms together, okay? Also, notice that when I drew this in the middle, didn't I draw that box at lower energy compared to the 1s atomic orbital? And generally speaking, you always do that, okay? Because when you form a bond, if it's going to form, it's got to be at lower energy than the atomic orbitals. If it wasn't, the bond would never ever form, okay? So generally speaking, increasing the electron density between the atom's nuclei is a good thing for potential energy of the system. And that's why we draw this box for the molecular orbital of H2 at a lower energy than the 1s state, okay? Everybody see that? And that's real important. So the shape of this figure, like this diamond shape, is generally always seen. And we'll see that throughout today's class, okay? Now, if I use 2 atomic orbitals, I need 2 molecular orbitals. I combine them in phase down here, or additively. Now I need the other case up here. I need my anti-bonding molecular orbital, where the wave functions combine out of phase. So what do I call that one? Oh, it's still a sigma, and on an overlap, it's still from 1s, but it's sigma star. We call it sigma star usually, sigma star 1s. And that's our anti-bonding orbital. That's the one that decreases electron density between the nuclei. That's at higher energy, much higher energy, right? Higher energy. And if we were to populate that with electrons, it would be bad, like worse than just having the 1s case, where the atoms are separated from one another, okay? So this is our diagram. All right, now, we would start this process by drawing these tie lines in, drawing these boxes, okay? What about the arrows? We haven't talked about that yet at all. So we're going to take these molecular orbitals, we're going to make them, and then we're going to put electrons into them, however many valence electrons we have to use. Now, each hydrogen brings 1 electron to the table, so we have 2 total. Okay, so what do? Just like we did in the atomic orbital case, we fill them in the lowest energy place possible and build up from low energy to high energy. We can only put 2 electrons in each orbital, molecular orbital. So 1, 2. 1 up arrow, 1 down arrow, spin quantum number +1/2, -1/2. And that's my molecular orbital energy level diagram for hydrogen. We've got 2 electrons in our sigma 1s bonding and no electrons in our sigma star 1s. Make sense? All right, now I can compute the bond order from that equation, which was on that previous slide. And what that told me to do was to take the number 1/2 and multiply it by 2 numbers that I subtract from one another. The first number was the number of electrons in a bonding molecular orbital. And the second number is the number of electrons in the anti-bonding molecular orbital. We've got 2 electrons in the bonding and 0 electrons in the antibonding. 2 minus 0 is 2. Multiply that by 1/2. Look, bond order of 1. And that's what we expected, of course, for our H2, is a single bond between the 2. Okay? More notably, if you calculate a positive bond order, that means that there is some net force holding the atoms together. And that molecule or substance of interest should have some inherent stability. Okay? May not be the most stable molecule known to man, but it would predict that this figure would predict that we could make it, we could bond hydrogen atoms together because of this. Okay? All right, now I'm going to throw a twist into the plot. I'm going to propose to you that I want to go to lab this afternoon and make a new molecule, a new ion, we'll say. And I'm going to go into the lab and I'm going to make H2 2-. It's a new ion, never before discovered, right? Now, what I'd like to do is to use this molecular orbital diagram approach to predict whether or not that would ever be possible to be made or not. Should I go do this experiment or am I just wasting my time, right? Well, how would I figure out? It wouldn't be so bad. I would draw the same exact diagram. Hydrogen atom on the left, hydrogen atom on the right. I would make my 1s sigma bonding orbital. I would make my 1s anti-bonding orbital, or my 1s star anti-bonding orbital. Same molecular orbitals. Everything about that story is the same. But how many electrons do I have in my proposed ion? Well, the hydrogens bring what, 2? And it looks like I've got 2 extra. So don't I now have 4? Right? So I've got 4 electrons total in this ion that I'm proposing to build and test. I got to put 4 electrons into my molecular orbitals then. So 2 down low in the bonding, but I still got 2 more to place, don't I? So 1, 2. That's 4. All right, so let's calculate the bond order of this one then. Before it was 1, but I think it might be different now. But what did we do to compute the bond order? 1/2 times, oops. One-half times what? Number of electrons in bonding molecular orbitals, which here is still 2. Got these 2 right here, right? Minus the number of electrons in anti-bonding orbitals, which is also 2. So what's my bond order going to be? 0. So that really quick analysis would allow me to predict that this ion is never going to exist. Because as soon as you get that second electron up into your anti-bonding 1s molecular orbital, your bond order is 0. Those hydrogen atoms, they'd rather be apart from one another than being together anymore, okay? There's no longer anything holding them together. That's the hydrogen is likely to decompose into atoms at that point. You're never going to observe this H2 2-. It's not going to exist because the bond order is 0. Okay, so this approach is going to allow us to figure out whether or not molecules or ions should be stable or not, okay? All right, so we considered some simple examples. I think the rest of class today here is going to just consider several more diatomic species from the periodic table. That's usually how this is presented, okay? So to summarize what we've done so far, we're going to build these molecular orbitals, and electrons are going to be placed within them, just like they were in atomic orbitals. Molecular orbitals are always filled from low energy to high. Just like the atomic orbitals, we can put 2 electrons in each molecular orbital, and only 2, as long as they have opposite spins, which generally they will, up arrow or down arrow, all right? Orbitals of equal energy will be half filled. We haven't seen that case yet, but you know how like where you had the like say 2p atomic orbitals, and you have to half fill them before you pair? Turns out very similar rule here, okay? Molecular orbitals of equal energy, we say that's degenerate. Another word that kind of gets thrown around. Orbitals of equal energy are said to be degenerate orbitals, okay? So you might hear that word at some point. But you half fill them until you have to pair them up. That's the same as what we did in the atomic orbital case, okay? And the molecular electron configuration then shows the type of molecular orbitals present and the number each contains, the number of electrons each contains. And just like we could write like 1s1 for a hydrogen atom, we can write a molecular electron configuration. And what that would look like for H2 for hydrogen would be this, okay? Which might be a little bit foreign to us, but we'd write sigma 1s with a 2 on top. Now that's not to say it's squared. That basically tells us the number of electrons in the sigma 1s bonding molecular orbital, right? And if we had some in the anti-bonding, we would just write sigma 1s anti-bonding and then write how many we had, all right? So that's basically what that designation means. It's kind of analogous to the SPDF configuration for atoms. All right, so let's move through the next few boxes on our periodic table, the next few elements. Talk about molecular orbital energy level diagrams for these substances and for the substances that we're going to refer to as their dimer, which basically means that we're going to try to pair up 2 of the elements together, okay? So we did hydrogen, H2. We knew that was stable. What about helium? Okay, could we make He2? No, I don't know. It's kind of weird. We've never seen that before. And helium's a noble gas. Usually we don't think it reacts with anything, right? But I don't know. I mean, maybe. Well, let's test out the idea. Using a molecular orbital energy level diagram. To do that, I'd like to consider this figure on the right of our slide. So we do the same exact thing we did for hydrogen. We figure out where the element is and what atomic orbitals, valence orbitals, are at play. And in helium, we've got the 1s atomic orbital for both helium atoms. Remember, helium atom number 1, helium atom number 2. 2 different atoms that we're bringing close together. Now, each of them have a 1s2 configuration from their atom perspective, okay? So that's what we write. 2 arrows in those purple boxes, right? Here and here. Now we bring those 1s atomic orbitals together. We combine them in phase or out of phase. In phase below, out of phase above, we draw a lower energy case and a higher energy case, as would be typical, right? And now we say, okay, how many electrons do we have? Well, I think we've got 4, 2 from each of our heliums, because helium atoms have each 2 electrons, so 4 total. And now we place those arrows into our boxes. 1, 2, 3, 4. 4 electrons, and all of our molecular orbitals are filled, both the bonding and the antibonding. And just like that last case now, our bond order would be 0. So do we expect He2 to exist? No, because its bond order is going to be 0, okay? All right, now I think I saw somebody had a question. Let me see if I can set up where you can ask here in a second. All right, I think that works. If you want to ask a question, go ahead.
The video cut out, so I couldn't see what you were writing, so I wasn't able to follow along.
Okay, did you catch back up?
No, I wasn't able to.
Is it still out now?
I can see the screen for the MO diagram of helium, but I can't see what you're writing on it.
Okay, so you don't see any writing?
No.
Okay. Here. All right, how about this? Do you see this at the bottom?
No.
No? Okay. All right, let me try one thing, all right? I'll be right back to the slides here. All right, how about now?
Yes, that works.
Okay, cool. I just reloaded it, so we're back on schedule here. All right, so we were just talking about this He2, and we came up with this molecular orbital diagram, and then we just placed 4 electrons in it, 2 in the bonding, 2 in the anti-bonding, and we said that the bond order had to be 0 for that, because it's 2 minus 2 times a half, that's 0. He2 is predicted to never exist. He is not going to bind with itself, okay, to form a covalent bond. It's just not. But what about He2 plus 1? Maybe we could take He2, steal an electron from it. Maybe that would exist. I don't know. But let's use our molecular orbital diagram to figure out. So He2, that's only got 3 electrons. He2 plus, I should say, has 3 electrons. Okay, the plus is the key here, because that means we've stolen 1 electron away from the He2, which would have 4. So we fill in our molecular orbital diagram with 3 electrons. Up, down, up. The third one has to go what? Into our anti-bonding molecular orbital, the higher energy one. But we did not pair this one, did we? Because we only had 3. So what's our bond order? Well, we take 1/2 times the number of electrons in the bonding molecular orbital, which is 2, minus the number of electrons in the anti-bonding. So isn't our bond order here 1/2? Kind of weird, right? We usually think of like single bonds, double bonds, but there's nothing that says we can't get a fractional bond order. And since it's a positive 1/2, stands to reason that, well, maybe this He2 plus 1, maybe I could kind of make that and get it to stick together for a little bit. Now, would it be the most stable substance? Maybe not, right? I mean, bond order is 1/2. That's not very formidable, but There's nothing that says that it's not possible to make that particular ion. Now this one's not going to work. Bond order 0 for He2, but if I take an electron away, it's He2 plus 1, and that's okay. All right, bond order 1/2. So you can kind of do a lot of things with these molecular orbital diagrams. All right, so now what we're going to do is we're going to start in the second period of our periodic table, okay? The one starts with lithium, and we're going to work our way across just to see a few more things, and then we're going to call it quits, okay? What about the molecular orbital diagram for Li2? This is 2 atoms of lithium bonded together. Is this possible? Is it not possible? Let's figure it out. Let's discuss it, right? So we draw in our energy axis, pseudo-quantitative, high and low, right? High energy, low energy, but usually no numbers. Like if you really get into this molecular orbital theory, by the way, and you use like computers to help combine these wave functions, you can actually get exact energies of these molecular orbitals, which is kind of cool. We just don't do that in this particular class, okay? So low energy, high energy. Now we're talking about lithium. And lithium has an electron configuration of 1s2, 2s1. So just like before, we're only going to use our valence electrons. So we're going to use the 2s atomic orbitals to make our molecular orbitals. We combine them in phase, out of phase. Now we have a sigma 2s. Notice it's 2s instead of the 1s. And a sigma star antibonding 2s. Now all we have to do, same thing. Lower energy, higher energy. Let's fill them in low to high with our electrons that we've got. How many electrons that we've got? How many valence electrons? There's 2 electrons in the valence shell for our Li2. Each atom brings 1 to the table. So 2 total. Up arrow, down arrow. Hey, look, that's a bond order of 1. So Li2 should be a completely viable substance. You should be able to make that and isolate it. Dimer of lithium, okay? What about Be2? This is the next element. It would have a electron configuration of 1s2, 2s2. We're still using our 2s atomic orbitals. We're combining them, dot, 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 on a tie line here, tie line, so on and so forth. Bonding, anti-bonding molecular orbitals, the 2s variety. It's still sigma because, again, you have the end-on-end overlap. Nothing's changed. Now, how many valence electrons do we have? Well, each atom brings 2 to the table, so 2 times 2 is 4. We've got 4 to play with, 4 to put into our molecular orbitals, and that's what we do. 1, 2, 3, 4. This is a bond order of 0, and Be2 is not going to exist, is it? Not going to happen. All right, so again, very similar to what we've seen so far. All right, so now let's go on to the rest of the elements in the second period of the periodic table. Boron through neon. We're going to do that in a second. But before we do, we are going to have to learn a few new things or modify this whole theory just a little bit, okay? Turns out we don't have to do much, but what we will have to do is start to play around with these p-type atomic orbitals now. So we're going to have to deal with that. But just like s atomic orbitals, we're able to combine in phase and out of phase to make our bonding and anti-bonding molecular orbitals. We can do the same exact thing with our p-type orbitals. They can combine in phase or out of phase. No big deal, okay? But there's an additional detail that we need to consider about the geometry with which our p orbitals will combine. And that's a little bit important, okay? This kind of goes back to that whole pi-type bonding versus sigma-type bonding that we talked about earlier class and then last time. Similar type of thing. Now, the one way or one geometry or the first geometry, that these p orbitals can combine in is a sigma type interaction, which is end-on-end overlap. That's shown right here. What if we have two adjacent atoms? This is atom 1 and atom 2, those black dots, okay? Those are the nuclei of the atoms. And each of them have p-type orbitals. Now, p-type orbitals are, again, these figure 8 or these dumbbell shapes that are shown here on the slide. So why couldn't the px orbital on the first atom overlap with the same px orbital on the second atom in an end-on-end fashion? Nothing that would stop that from happening. We can combine them in phase, we can combine them out of phase, but that's a sigma type interaction, end on end. So because of that, when those types of orbitals combine, why don't we make a sigma? In this case, we're going to call this a 2p because it's generated from a 2p atomic orbital. But it'll be a sigma 2p molecular orbital. That'll be the bonding case. It would look like this right here. You see how there's that gray shaded area between the nuclei that's now like, I didn't have it like bigger, but really what that would correspond to would be like a region of higher electron density between the two nuclei, and that's good for bonding. And then if these p orbitals from the atoms over here combine out of phase, we'd get a node between the atoms, a region of 0 electron density. And then this one would be our sigma 2p star. That one is an anti-bonding orbital. Remember, anytime you see the asterisk, it's anti-bonding, right? So we can use these, extend the deal here with these p orbitals, just like we've been talking about, right? Combine them in phase, combine them out of phase, bonding, anti-bonding. It's just that the geometry is just a little different here, okay? But this is still a sigma type interaction. All right, now we're going to talk about where it gets really different, and that's on the bottom of this slide, okay? These are going to be pi type interactions. And the reason why is because when I take atom 1 and atom 2, and I bring these two close together, these p lobes can still interact here and here. But this is like what I like to call side-on-side overlap. That is a pi bond, side-on-side overlap. Rotation would not be allowed around it. Now again, nothing says that we can't combine our atomic orbitals in phase and out of phase. So we're going to do that. We can make a bonding molecular orbital that looks like this. That would be where they combine in phase. And we can have an anti-bonding molecular orbital with a node between the nuclei. That will be out of phase, just like we've been talking about all day, okay? But because this is a side-on-side overlap, the molecular orbitals have a little bit different shape, right? Makes sense? It's a pi-type interaction. That's a big difference, okay? So it seems like maybe we should give these orbitals a different name, okay? This isn't a sigma-type interaction. It's a pi-type interaction. So what we're going to do is we're going to call the one on the bottom a pi 2p bonding molecular orbital. And the one on the top is going to be a pi star 2p. 2p is because we're using the 2p atomic orbitals to make this, okay? But this one is our anti-bonding. And just like we could with our sigma, we're going to be able to put electrons into these bonding molecular orbitals and anti-bonding ones, okay? Now let me ask you one more question before we move on. Okay. I've described this pi-type interaction between the p atomic orbitals and the overlap of them, okay? What I'm wondering is how many of those do you think we're going to have? Now there's one that's drawn here where these py orbitals overlap, right? Would there be another one that's maybe not drawn? If you think about the p orbitals, okay? Think about your Cartesian coordinate system. Now let's talk about the p orbitals. There's one that would be like a figure 8 shape in this dimension, right? Because there's 3 p orbitals. There's another one that would be up and down. And then lastly, there'd want to be one that's front and back, right? Now this is one of them. The sigma type interaction is the other, right? The sigma type interaction would be like if there's a second atom, like here, and the greens overlap, that's like my sigma, right? Now, if there's a second atom, maybe my yellows could overlap. And that might be like one of these, right? That's a pi type. But what about the blue? See if I can draw it in this dimension. Couldn't the blues also overlap in that third direct dimension, right? So while one of these is drawn, it turns out there can be two, or is two, pi type molecular orbitals. There's two bonding and even two anti-bonding, okay? And the only difference between them, I mean, they look kind of the same, right, is what this picture shows. But the difference between them is in they're arranged along different axes in our Cartesian coordinate system. That's the only difference between them, okay? They are also degenerate or equal energy, the pi type. Now, that's not to say the pi type are equal in energy in the sigma. That's actually not true. It turns out that the sigma 2p and the pi 2p, their energies are not equal. They're not the same, okay? And we're going to see that in our molecular orbital diagrams here in a few minutes. All right, so now that we understand that a little bit, we talked about it some, let's move across that second period and talk a little bit more about what molecular energy level diagrams would look like as we move from left to right across the period, okay? Now, I just mentioned that the energy of the sigma and the pi type molecular orbitals for the p orbitals are not the same, okay? We're going to see that in this figure. So I'm going to draw a line down the middle. Now, what I'm going to discuss first is on the left, okay? And I'm going to refer to this, for lack of a better term, as the normal case, okay? This slide is actually much more complex than you ever want it to be, and we'll get through it, okay? But there's going to be what I call a normal case and a not so normal case. And that's going to be analogous to without something called SP mixing or with SP mixing. And I'm going to call this the unusual case. Okay. It turns out that there's only a few elements in the second period of the periodic table that this applies to. So if you're going to ever make a molecular orbital energy level diagram for boron, carbon, C2, or nitrogen, you have to use this unusual case, okay, which we're going to get back to here eventually. But more generally, I'd like to talk about the normal case on the left, because this is, for most elements, what you would encounter, and it's kind of the typical case. So let's look closely at this diagram. Again, we start with our energy axis. Now, if we're starting to talk about elements boron, carbon, nitrogen, the rest of that second period, and we want to predict whether B2 or C2 or O2 can exist, we start getting into the situation where we have both 2s and 2p atomic orbital electrons. In other words, we start putting electrons into both the 2s and the 2p. So to this point, we haven't done a whole lot with the p. I mean, on that previous slide, we kind of explained in space how the overlap could occur, and that's great because we're going to use that here. But we haven't really seen examples where we integrated p electrons in. So we're going to have to do that now. So in addition to making molecular orbitals from our 2s, remember the molecular orbitals are the gray ones in the middle, right? So we have atom number 2, atom number 1, and the molecular orbitals are in the middle. So in addition to making my 2s bonding and anti-bonding, sigma type, I'm also going to need to use my p-type orbitals, or my p-type orbitals, okay? So I'm going to use my 2p, and it looks like I'm going to take 3 of my 2p from atom 1, 3 of my 2p from atom 2, make molecular orbitals. So I need to make 6 molecular orbitals from just my p atomic orbitals. So where do they all come from? And what are their relative energies in the normal case? Well, the lowest energy molecular orbital generated from my p-type interactions is my sigma 2p bonding. That is the one where the p lobes combined end on end in phase. Sigma 2p. That's the lowest in energy in the normal case. So we only draw one box for that, notice. Everybody see we have one box? And the reason for that is pretty simple. Only one set of our p orbitals can overlap in this fashion. Only one, and once that's done, that's it. But the next higher in energy orbital, usually a little bit higher, are my remaining bonding molecular orbitals, but these are pi 2p. Now there's 2 boxes there, right? Why is that? Well, that's not a very good picture. One of my figure 8s could overlap side on side. And then in the other dimension, this would be along another axis in my Cartesian coordinate system, maybe the one that goes into and out of the screen. I get interaction side on side in a different dimension. Okay, so this is the side on side overlap, right? That's what defines pi bonding. So it's a pi molecular orbital. It's a 2p because it's generated from the 2p atomic orbital. That's where it came from, the ingredient list, right? It's a bonding because our orbitals right now are combining in phase. But notice that there are n equals 2 of them. Well, that's because this is one, this is the other. They're equal in energy. They're just orientated on different axes. Pi type bonding, okay? Make sense? Awesome. All right, now those are the ones where we're combining those p atomic orbitals in phase. But there's a couple others up here. The ones up top are our anti-bonding molecular orbitals that result from p-type interactions. Well, one's a sigma type interaction, but they're when we combine the p lobes out of phase. So the next in energy are these 2 right here. Those are our pi star 2p. So think about that. Pi tells you the type or geometry of interaction, the side on side, the p lobes. The star tells you it's antibonding, so you're combining them out of phase. And the 2p's, where they're coming from, what atomic orbitals. Now there's 2 boxes there because again, there are 2 geometries of this pi-type interaction. And then lastly, the highest energy is our sigma star 2p. Sigma star 2p is the molecular orbital, which is an anti-bonding orbital formed from the sigma type interaction of our atomic p's. This is the end on end, and that's the highest energy case. That's where they just combine out of phase, and it's not good for bonding, but it's one of our molecular orbitals, highest energy one. Okay? Now, what I'd like you to consider here for a second is that this ordering of the molecular orbitals in the middle in terms of their energies from high to low, that is what I'm going to call like the normal ordering, okay? in period 2 of the periodic table, we apply that scheme in ordering to those elements, oxygen, fluorine, and neon, the latter elements after oxygen, okay? Heavier ones. But just to make life more complicated than it already is with this, right? It's kind of an abstract concept, right? But just to make life a little bit more complicated, there's kind of a monkey wrench thrown into nature, okay? And this monkey wrench is typically referred to as sp mixing of molecular orbitals. We don't need to know, I guess, all the details of this, all right, from a physics perspective. But sp mixing is a phenomenon by which these 2s and 2p atomic orbitals are kind of close together in energy and spatially. So they end up kind of mixing or blending, influencing one another, we'll say. And the net result of this is going to be shown right here. It's highlighted now in purple and gray, okay? So there's not a whole lot of change down here below in our 2s. The energies of those orbitals do change a little bit. This 2s actually drops a little bit relative to the way it would otherwise, but the filling order is kind of the same, right? You start with your bonding sigma 2s, and then you move to your anti-bonding 2s, right? And that's the same order, at least, as what we saw on the left. But where things really get switched up is right here. Look at what happened from the normal case. The normal case was our sigma and then our pi. But in the case here, with this sp mixing, the pi comes first, and then the sigma. Okay? So these two, in the case of sp mixing, just flip-flop. And that is the weird circumstance of this, okay? Now again, we do this for these three elements once you get beyond nitrogen on the periodic table. Once you get to oxygen in the second period, things go back to the normal case. And you say, well, why is that important, right? Well, what we're going to do now is we're going to start filling in electrons and building these molecular orbital energy level diagrams for these other elements. And to do that, we have to fill from lowest energy to highest energy. So the ordering becomes actually really quite crucial, okay? That makes sense? All right, so let me see what other slides I have. We may have to come back to this one. Oh, this one works, okay. All right, so what this slide does for us, then, if I can get it just right, is it considers the remaining elements across that second period and what their molecular orbital energy level diagram would look like, okay? So B2 is our first element. It's got a 1s2, 2s2, 2p1 atomic configuration. There are 3 valence electrons per atom, right? So now we're starting to mix in these p-type atomic orbitals. So what do? Well, we write a molecular energy diagram, or a molecular orbital energy diagram that looks like this. We start down with the 2s. We call this the sigma 2s and the sigma star 2s. That's here and here. Those are our lowest energy cases. And now we're going to blend in some p's. But boron, being a lighter element than that cutoff, right? Right here is that cutoff where we have to reverse the order. Being a lighter element means we have to reverse the order. So the pi comes next. So line, 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 line. Now these are my 2p atomic orbitals. So what I'm going to do is here and here, create 2 lines or boxes basically. And I'm going to call those my pi 2p bonding. Now those come first in the case of the sp mixed. And then after that, comes my 1 bar. That's going to be this one, my sigma 2p. I go a little bit higher in energy. And that's where I'm going to encounter my pi 2p star, my antibonding. And then even higher in energy yet, it's my sigma 2p star. And that will be my molecular energy level diagram that I draw out, okay? Now, we're doing B2. Each boron atom has 3 valence electrons, so 6 electrons total, right? So I start low and go high, right? Kind of like an auction or something. So 1, 2, 3, 4, 5. I don't pair until I'm forced. 6. Make sense? Y'all with me on that? All right. Now let me ask you this, and I'll make your life easier here by circling these electrons. Would you expect B2 to be paramagnetic, or the other option, which is diamagnetic? Now, way back when we studied this, right, this was whether or not atoms interacted with a magnetic field or not, right? Whether they were attracted to a magnetic field or weakly repelled. Paramagnetic is when they're attracted to the magnetic field. Diamagnetic was when they're not, okay? And for atoms, remember what was important was whether or not they had unpaired electrons. If they do have unpaired electrons in atoms, we'd say it was paramagnetic. It would be attracted to a magnetic field. Molecules actually behave the same way. So for this one, B2, would you expect it to be paramagnetic or not? And why? I think it's going to be paramagnetic because look, it's got unpaired electrons. Now that's not saying boron as an element. I'm saying B2, this molecule, if we make it, would be paramagnetic because it's got unpaired electrons in its molecular orbital. Make sense? So we can do that kind of analysis then, whether or not this substance will be attracted to a magnetic field or not, just again, based on these particular diagrams, okay? And taking that even a step further, let me do a little bit of erasing here. What if, so this would be the ground state for B2, right? The ground state or lowest energy state. What if I decided, maybe I should use a red marker. What if I decided that I wanted to take, oops, I'm on eraser, okay. What if I decided that I wanted to take this electron in my pi 2p orbital, and I wanted to do an electronic transition? I'm just going to take it to the pi star 2p. So I take that electron and I move it up here. Now clearly there's an energy gap there. I move it to a higher energy place, right? There's a delta E or an energy gap. But what if I decide to bridge that energy gap with a photon of light energy, which I'll call h nu, right? Because that's the energy of photons, h times nu, frequency times Planck's constant. So I could go from that spot to that spot, and that would be light absorption, just like we have light absorption in atoms. And if I was able to actually compute the exact energy of that molecular orbital and the exact energy of this one, I could compute the gap between it, and I'd know what color light B2 would absorb well, right? I could predict its electronic spectra or its light absorption spectra from this type of diagram and this type of information, right? So that's kind of like when you really get into molecular orbital theory, what people are really able to do with all this, all right? Now, just to kind of finish off this slide, let's move across that second period of the periodic table in the remaining minutes that we have today. if I was going to do this analysis for C2, which is 2 atoms of carbon bonded together. Okay, now carbon on our periodic table will be 2s2, 2p2. So each carbon atom has 4, and we've got 2 of them, 8 electrons to assign. Again, carbon is lower than that cutoff, so we're going to do our mixing, our sp mixing. The ordering is the same as it was for the B2. So we put 2 electrons in our sigma 2s, 2 in our sigma star 2s, 4 more in our pi 2p, and that ends up making 8, all right? Everybody see that? So that's where they would go. Now, what would you expect the bond order of this one to be? What would be the bond order of that one? Any ideas? What is it? 1/2 times number of electrons in bonding minus antibonding. Okay, so 1/2. How many electrons do we have in the bonding right now? Let's see, we got these 4 plus 2 here. I think it's 6 minus 2. All right, so that would be a bond order of 2. Okay. So C2 seems like a pretty viable substance. Like we could actually like make that, okay? All right, so that's interesting. What about N2? This is our good friend nitrogen, right? Gas in the air. Now nitrogen would have a 2s2, each atom would be 2s2, 2p3. So that's 10 electrons when we make the N2. So again, we're sp mixed. This is the last element. That's sp mixed. So 2, 4, 6, 8, 10. All right. Now notice what we did there. We put the 2 extra electrons into a bonding molecular orbital. So what about nitrogen's bond order? It's 1/2 bonding electrons minus non-bonding. So let's see. I think these are our only non-bonding, right? So we're going to subtract 2. All right, so let me erase everything else and maybe use a different color marker. So 2, 4, 6, 8. So what's our bond order? Isn't it 3? And sure enough, if you draw this dot structure of nitrogen, that's in agreement. Triple bond. Now what about the other elements? O2, F2, and E2. We're just picking up more electrons. And we now pass that threshold for the normal case. So now we're no longer sp mixing. It's normal now, okay? So our filling order changes. First 2 are the same, sigma 2s, sigma star 2s. Now we use our p's. Sigma 2p, pi 2p, pi star, sigma star 2p. That's the only difference. The order changes right there with oxygen, right? Oxygen heavier, it goes back normal. So for oxygen, we'd have 1s2, 2s2, 2p what? 4, yeah? That's 6 valence electrons per oxygen, 12 total. So 2, 4, 6, 8, 10. Now I got to fill in this box. Notice how you do it individually. You don't pair, right? But that gets me to my 12 once I'm there. But you notice those arrows, they weren't paired. They went in individually first, right? And that's pretty important actually for one property of oxygen we'll talk about here in a second, but that's using 12 electrons. What about O2? So that's O2, right? Oxygen gas. Paramagnetic or diamagnetic? Wouldn't it be para? Because it's got unpaired electrons, right? And interestingly enough, if you like do some searching on the internet, you can find like movies and images of I think liquid oxygen. If you cool it down enough, kind of being like suspended in a magnetic field, it's actually attracted to magnets, okay? Because it's got unpaired electrons. It's paramagnetic, okay? So we can do this for every element. Fluorine just adds a couple more electrons, 2 more, so that would be diamagnetic. And then Ne2 would add 2 more electrons yet. And all these would cancel each other out. So Ne2, that's not going to be stable. Bond order 0, right? So this type of analysis can really be done for these elements in the first and second periods of the periodic table. You can also do it for these. We'll probably have to come back and talk about this next Tuesday, but we're almost done with this chapter as it turns out. So if you wanted to actually work on chapter 11 Connect this weekend, I don't really think there'd be a lot that would stop you from doing that. And by taking a little bit of a look at the book, I suspect you could get through it without much trouble because we actually described almost all we're going to about molecular orbital diagrams, okay? But I'm out of time, so I'm gonna stop talking and I'm gonna send you on your way. Everybody have a good weekend. If anything does come up, let me know. And remember, we're going to start our big transition here, the online class, okay, here for the Thanksgiving period. So I don't think it'll be too difficult to do that. It's something we've kind of been doing all along. So I suspect we're all used to it now. But if anything unusual comes up, please let me know and we'll talk to you all next Tuesday at the normal time. See ya. Bye.